Welcome back, class. So today we are going to start our discussion of chapters 8 and 9. So these two chapters we'll be putting them together in our discussion. And so these chapters talk about the development of models to understand better the behavior of the electron. So we saw earlier how Rutherford gave us the nuclear model of the atom, which really sort of sets the stage for the nucleus, right? That part of the atom, but sort of left electron behavior as, sort of a very vague concept about these negative electrons somehow existing around the nucleus. In this chapter, we're going to dive into models that allow us to gain a better understanding of how those electrons behave. Now, the most common model, the most current model, and what we'll work towards understanding is what's called the quantum mechanical model. So first we'll build into this in chapter 8, and then we'll sort of explore different aspects of this in chapter 9 when we look at how these things can affect the behavior of the elements in chapter 9. So we get started, we're going to go into chapter 8, and again, we're going to be discussing the quantum mechanical model of the atom, or our build-up toward understanding this model. Now, I will state out front that this is an extremely complex model. The mathematics involved are way beyond the scope of a general chemistry class, and thus we will be touching on the ideas, we will be doing some calculations, but we will only sort of be scratching the surface of the mathematics involved in doing this. Now, before we get too excited and jump into the behavior of electrons themselves, we're first going to explore the nature of light, what we consider light. Now, the reason for doing this is it turns out that during the development of the quantum mechanical model, it was found that the electron behavior, the behavior of electrons, had many characteristics in common with the behavior of light. And so we're going to spend the first part of this chapter understanding how light behaves. Now, the first thing that we can think about with light is that it is a wave, right? So light exists as a wave. Now, light is a euphemism. It's a common term for what is more commonly known, or more specifically known as electromagnetic radiation. Now, electromagnetic radiation consists of waves, electromagnetic waves. So what these are waves that consist of both an electric field and a magnetic field. And those two field components exist perpendicular to one another. And so you can see here sort of the idea of an electromagnetic wave, where we have these oscillating magnetic fields and electric fields. Now, we don't need to, in this course, get too tied up into the idea of, electromagnetic fields and electric fields and magnetic fields. We can simply view this as a simple wave, right? Something like that might be drawn here. Now, some of the key properties of electromagnetic waves we need to understand is that electromagnetic waves move through space at a constant speed of 3 times 10 to the 8 meters per second, or what we more commonly know as the speed of light. Now, we should understand that this speed is in a vacuum. And so that means that when it's moving through Earth's atmosphere, it's traveling at a slower velocity. But the velocity is not enough different that it makes a big difference in any kind of calculations that we would do. So we just think about electromagnetic waves as moving at the speed of light. Light waves, right? Now, how fast is this? Well, 3 times 10 to the 8 meters per second is the equivalent of about 186,000 miles per second. And so it's fast, right? Now, some other waves you might be familiar with are something like sound waves, right? So sound waves are traveling at about 300 meters per second. So about 1,000,000 times faster, right? Light waves are traveling about 1,000,000 times faster as a sound wave. And this is why you may have experienced the phenomenon of something like lightning or fireworks, right? That you see them before you hear them. And this is because the sound waves are moving much slower than the light waves. So the light waves reach your eyes before the sound waves reach your ears. Now, a wave is characterized by several properties. So the first one that we're going to talk about is what's known as the wavelength. So wavelength is abbreviated by the Greek letter lambda. Whoops. Which sort of looks like this upside down Y. And it's simply a measure of the distance covered by the wave. So we typically think about it as the distance between crest and crest, or you could measure it between the bottom parts of the wave and trough, right? And trough, right? But again, it's going to come up with the same distance. So it's the distance between wave peaks, right? So the wavelength is one way that we characterize a wave. Now, another property is something called the amplitude. Now, the amplitude is simply the height of those waves above a center point. So if we see the center line running here, the amplitude is how high the crest is above that line, or how below the trough is below that line. Those two things are going to be the same. Now, in terms of light, the amplitude could be considered a measure of intensity, right? Or brightness. The higher the amplitude, the brighter or more intense the light would be. So we got wavelength and amplitude as two important characteristics of light waves. Now, a third characteristic is what's known as the frequency. So the frequency, which is abbreviated by what is the Greek letter nu, which looks like a V, but is not actually a V. It's, again, a Greek letter nu, but a lot of times you'll see it drawn as sort of an italicized or sort of a strange-looking V. And it is the number of waves that pass a point in a given period of time. Usually that is a second. And so we see that the units of wavelength are what we call reciprocal seconds, or 1/seconds, often written as seconds to the -1. Another common unit of frequency is going to be the hertz, which is equal to a reciprocal second. So you'll see one of those two units when we talk about frequency. And again, this is how many crests or how many waves pass by a given point per period of time. So we might imagine having waves and we're staring at a point and we're just counting the number of crests that pass that point in a given period of time, say every second. Now, one thing that we want to understand is here, as we adjust the wavelength, so as the wavelength becomes smaller, so as you go down here, right, the wavelength is getting smaller, what we should see is that the frequency is going to become higher. Right? So the closer the waves are, the more that we're going to see in that same given period of time. And so what we say is that the wavelength and the frequency are inversely proportional. As one goes up, the other one goes down. So as wavelength goes down, frequency goes up. Now, we can write this as an equation by saying that the frequency is equal to the velocity, the speed of light, divided by the wavelength. So this equation represents that inverse relationship between frequency and wavelength. Now, when we think of light, we often think of light that we can see, right? What we'll come to term as visible light. And the color of that visible light is determined by its wavelength or frequency, right? Just depends on how you want to view it. Now, I will say most of the time the way we refer to different colors is based on their wavelength. So that's kind of how we'll most commonly refer to it. But you could just as easily refer to it as frequency because of the relationship between wavelength and frequency. So, summarize, we have waves. The key properties of those waves are its wavelength, right, which is the length between waves, right, typically measured in some unit of length, like a meter or some other unit. We have the amplitude, which gives us an idea of how bright the light is, how big the waves are, and we have the frequency, right, which is how many waves pass by a given point every second. Now, we were talking about wavelength and frequency. We can look at a problem here and try to apply this equation. So, remember our equation here is frequency equals the speed of light over the wavelength. So in this case, we're given a wavelength of 515 nanometers, and we need to calculate the frequency. Now, remembering that c is the speed of light, 3.00 times 10 to the 8th meters per second. Now, because speed of light is in units of meters per second, we need our wavelength in meters. So if in the problem it's given in some other length unit, we need to first convert it to meters. So if I start with my 515 nanometers, I can use my metric prefixes, and if I remember, 1 nanometer is equal to 1 times 10 to the minus 9th meters. So my nanos cancel out, and I do my math. I get 5.15 times 10 to the minus 7th meters is the wavelength. So now I can plug into my equation for frequency, and I get 3 times 10 to the 8th meters per second divided by 5.15 times 10 to the minus 7 meters. Of course, my meters cancel here, and what I'm left with is my result, which is 5.83 times 10 to the 14th. And again, what are my units? Well, I have just division by seconds, or seconds to the minus 1. Or we could also write this as hertz. So my frequency here, 5.83 times 10 to the 14 reciprocal seconds. So we have, a lot of waves passing by this point every second. Okay, so let's turn our attention back to looking at the general properties of waves, and we were looking at the idea of color. Now, color is an interesting phenomenon because it is a human phenomenon, right? It is how our brain has sort of rationalized or allowed us to understand when we observe certain wavelengths of light. Now, the human eye can observe a certain span of wavelengths. Now, we'll see that span of wavelengths is about 450 nanometers to about 700 nanometers in wavelength is what the human eye can perceive. And within that, we're going to have the various colors of visible light that we can absorb. So when we see white light coming from, say, the sun or a standard incandescent light bulb, right? It's a mixture of all the colors of visible light. And it's what we call a continuous spectrum, sometimes called a rainbow spectrum, right? Because that's what a rainbow is, right? If we've seen the rainbow, or when light passes through a prism or some sort of crystal, right? The white light gets separated into all the colors of light. And this follows our acronym Roy G. Biv, right? Or red, orange, yellow, green, blue, indigo, violet. Right? So we go all the way from red at one extreme to violet at the other extreme. Now, in terms of the range, right, violet is going to be down here, right, at the lower wavelength, and red is going to be up at the higher wavelength that we can observe. So, color is a way that our brains can distinguish the different wavelengths of light that we're observing. Now, what about when something looks a certain color or appears a certain color? What does that really mean to us? Well, when we absorb light, when an object absorbs light, right, that means it reflects some of the wavelengths of light, and it absorbs other ones. So if some object, because of what it's made of, or the chemical dyes that it has inside of it, right? Those dyes are just chemicals that absorb certain wavelengths of light. And so if it absorbs certain wavelengths of light and reflects others, what we observe are the wavelengths that are reflected, right? Because if, for example, this red sweater, right, that contains some sort of red dye, if that dye has the property of absorbing all of the colors of light except for red wavelengths, then what reflects off of that object and reaches our eyes over here, right, is only the red light. And so it appears red to us. So what we're actually observing when we see something as a color is we're observing what wavelengths of light, or the combination of wavelengths of light, that are reflected off of that object. So if something appears white, that means that it reflects basically all the wavelengths and absorbs very little. If something appears black, that means it absorbs pretty much everything and reflects almost nothing. And so when no wavelengths are reflected, we see that as black. When all wavelengths are reflected, we see that as white. When we see colors, we're seeing the combination of wavelengths that make those colors. All right, so color.